Nice. Hello everyone, it's May the 9th. It's a Sunday, so so it's going to be a interesting one today, I hope. All right, let's take a look. We have some response. We did post a solution yesterday. I don't see anything here. It's minimum Windows substring. No, that's not the one that I think nobody commented on it. That's fine. Oh, this one. Did I comment on this? That's 2 days ago. Delete operators for two. Doesn't matter. All right, let's go for it. Let's see what we have. Construct target array with multiple sums. Okay, given an array of integers target from a starting array, A consisting of all ones. Okay, and then perform the following procedures. Let x be the sum of all elements currently in an array. Choose index at I such that, okay, and set the value of A at index I to x. Repeat this procedure as many times as needed. Return true if it is possible to construct the target array from A, otherwise return false. Let me understand again. So we have starting with all ones, right? And you may perform the following procedure. Let x be the sum of all elements, so 3. Choose index, we'll choose an index inside, and then place a value, we'll place 3 in it, and then sum it up again, place it in it, sum it again. Oh wow, you can do it that way, wow. Impossible to create, yeah, because the minimum is 4, right? 8 and 5, so it's going to be 1, 1. So what can we do with the 1, 1? So first round we get 2, second round, no matter where we put it, second round we get 3. The third round, well, we don't have to put it, we can put it in the same place. Third round is 5, we get a 5. Last round we get an 8. 8, 5. Okay. I see how this is going. Seems to be complicated in terms of the operation. But the first step is sure. The first step is deterministic. We get a sum, which is the length, right? Which means if inside the array we have any value that is smaller than a sum, then there's no way we can achieve it. So that's this situation. We return false immediately. So we have to see. This could be like a first check. We just go through the target and find the minimum. I don't have to go through the target, we just find the minimum. And if the minimum is smaller than the length of the target, then it's a false. No question about it. Now if it's larger, then we find the minimum. We'll still find the minimum, right? We find the minimum of them. And from that, we can determine how we reach it. Because as we progress, right? As we progress in this procedure, each time we compute the sum and then we replace some value, and the value we replace will always be smaller than the sum. So every procedure will produce a larger value. So the smaller value, the smallest value, will be the first one we will compute. So we find the smallest. We can even put that into, let's say, a priority queue. So each time we can pop out the smallest. So we get the smallest value, right? We get the smallest value. We also need its position. So it's going to be priority queue with a tuple, right? And then the first position will be the value. The second position will be the index. And we find it, right? We know the value. And after we learn the value, we need to see if it's possible to construct it. Now that depends. Like in this case, it's a 3, and we know the sum of initially that's a 3. So we say that's possible. So we say after this we put 3 into the second position. That's done. Next, the smallest is 5. So we need to find 5. The current sum is 5, so that's good. We put it into the position. The next one is 9. Current sum is 9. Great, we put it in the position. Then we say it's done. Good. Second one, 2 is smaller than 4. We're not doing it. This one, and we include multiples, right? So, yeah, it's deterministic. We have to get the smallest first. If we do not find the smallest, then we can never go back. So it's step by step. So first we pop out 5, which is at position 1. So we know we need to get 5 and put at position 1. However, currently the sum is 2. We say, okay, we get 2, put it anywhere. Doesn't really matter. I put it anywhere. And then the sum is 3. And we say, now we have a choice, right? Sum is 3. We can, it doesn't really matter if we replace. Oh yeah, it doesn't really, hold on, does it really matter? It might not. Like we get 3 out, we say we can replace any value, right? So we can replace any value. It didn't say that you cannot replace the value you have replaced before. It just said an index, any index. So we can replace 2, or we do not replace 2. Let's see if it's if we replace a value we already have. It's the same. So because every time you sum them together, right? You sum them together, and if you replace it, you're still summing them together. If I replace the ones I have summed together before, or I do not replace them, it's the, hold on, let me see if it's the same. So a bunch of 1s, and then we have a sum, right? And then I replace the 1 with it. Well, I think it does matter, right? It does matter. But eventually it's just multiple 1s, right? Every value can be computed, I think. Every one can be computed. Let's look at this. If it's 3, we replace it. If it's 5, we replace in here. Then it's a 7, we replace here. And we get a 9, but we never get the other values. Because I can see a situation where like, let's say 1 of 4, right? 1 of 4. If a 1, 1, we want to get to a 4. So add it together, and then add it together is 3. If I replace 1, then we can never get 4. So once we get a value out, right? Once like we get a value, we add them together as 2. Then we need to decide which one to replace. Then we need to look inside the current values and see if we can make it. Is that true? Okay, let me think again. 3 requires 3 1s, that's 3 1s, right? And then 5 requires 5 1s added together. And we have 3 1s, which means we need 2 more 1s, like 2 rounds. Because I cannot like just each time, look at the target length. It's huge, right? It's a huge length. So, and you see this, right? I cannot sum them all the time. We can get a sum out, okay? So we sum them together, we get a value out, and based on the value. Hold on. Let me think again. Every time we get a sum, we get a value out, and we replace it, replace any one inside, and then we sum again. But what we can say, if every time we replace is the maximum, the fastest way to reach a big value is each time we replace a 1, right? Then we can accumulate a value faster. And if we do that, basically what we mean is we get a sum and we replace, and we don't replace. Basically, we just get a sum and we do sum minus 1, so that's the value we can keep. And then we do the same sum again, all right? And then minus 1, that's the one we can keep. And we just see how fast we can reach the target value. We have a target value, and then we can sum them together. All right, we sum them together, get a value, sum them together again, we get another value. Yeah, like if we sum them together, that's 3. Sum them together again, that's 3, that's 6. But we have to, the ones that we can do is 2 plus 3, right? And then that's going to become 5. And if we want to do again, then we'll do, what's that, 4? No. Sum them together is 3. So each time, if we sum them together, it's 3, right? And we say we can reach 3 by doing it once. We can reach 5 by putting 3 back. So the next time, it's actually 2 is adding to 3. That's 5. And then if we put, then we put 5 in. So we actually doing a 4. That's 6, right? That's 6. 2 plus 4 is 6. So 1, 3, 2 is 6. That's exactly we add 2 times. Yeah, we'll add them together, put it in, right? And then we add them together again. That's 3 ones. And if I add them together, hold on, isn't that add them together? Oh, and that's not 2. No. 3 coming in, 5 coming in, add them together. This is 5, so we start with 3, and then this is 5, and this is 9. But we do it twice, it's going to be 6. But we do it 3 times, it's going to be 9. Hold on. Think about it some other way. So the goal is to reach this, right? The goal is to, let's not think about all these. I just think about the goal to reach the smallest value, right? The smallest value. So we have smallest value, and we have a bunch of 1s. The question is, how do we reach the smallest value? Given the value, we want to sum them together, do whatever magic. So basically, there are 2 ways, right? So we sum them together, and we need to replace something. Or sum them together, we get a sum, right? And then we need to replace something, right? Replace something. So we can say currently we have 1. How many 1s we have, right? So we're going to start. So we have 2 1s. I'm looking at this example, right? We have 2 1s to start, and we want to sum up to 5. So 2 1s start. So we're going to do first round. Add them together, we have to get 2, right? So after I get 2, we have a choice, right? So one of the values needs to be replaced by 2 in order to reach the solution. One of the 2 need to be replaced, right? So we say based on which one we want to replace, we can replace one of them. So and then we have the remaining. So we'll look at 5, right? And then we say 5, we sum is 2, and 2 is not 5, right? So we want to increase more. So we say replace the smallest, right? We replace the smallest. And after we replace smallest, we do it again. We sum them together, that's 3, and it's still not reaching 5. And then we also replace the smallest, and we try it again. And if we explode, okay, we always replace the smallest value currently, and I will always replace the smallest value that's currently available. So we minus that, and then we plus the new one, so we get a new value. And if that explodes, then we backtracking. So replace the second smallest, right? If we replace the second smallest, and how do we do the second smallest? We pop it out. That doesn't seem, because the second smallest is hard to come by. You have to pop it out to get the second smallest, replace that, and then compute again. And once we get it, then that's it. We're gonna go for a new round. Right? A new round. And also I realize it's impossible to have a value that's the same value. You cannot achieve the same value. Or can we? No, because each time when you sum, it's going to be bigger. So each value you get will be bigger than the previous one. So if the target has repeats, and that's also not good. That's also not going to work. So it's not only minimum, but also if they have repeats, we can exit immediately. But if we replace the smallest, it's not working. Hold on, can we do it the other way? Right? So we have 8 and 5. So we know if we want to get to 8, it has to be 5 plus something. Right? 5 plus something, or whatever remaining, plus a value, and then we'll replace the value with 8. Right? So from there, we know 8 must be replaced by a 3. Now it has 3 and 5. So we do 5. How do we get to 5? It has to be 3 plus 2 to get to 5. How to get to 3 must be 2 plus 1. How to get 2 must be 1 plus 1. Now we can go back to 1, 1. That's good. That's good. If we have 1, 1, 1, 2, the largest 2, I say how to get 2 has to be 1, 1, 1, 3 plus something. And it's already large, so this is impossible. 9, 3, 5. To get 9 has to be 3 plus 5 plus something. So that's going to be 1. How to get 5? It's going to be 1 plus 4 plus something. It's going to be 1. How to 3? It's going to be 1 plus 1 plus something. And then we can go back to 1, 1. Yes, we do a reverse style, going from largest to smallest. Okay, so we can sort it, and we don't care, right? We can sort it. We don't even care the position. We sort it with the largest at the beginning, and then we pick out the largest, and then we replace it with whatever value. That's actually not true. That's actually not true. We have to still give it as a priority queue. It's still going to be a priority queue because every time we're going to pop out the largest. So we pop out the largest, and we also have the sum of everything. So 935, the sum is 17, right? So our sum is 17. And now we'll pop out 9, right? So 9 must be 17 minus 9 is going to be 8 plus something to get to 9, right? And if that something is smaller, So first of all, this 8 has to be 8 has to be smaller than 9. So we do 8 minus 9, 9 minus 8. So we know we need a 1 to get to 9, right? So we say we need a 1. All right. So we have found the first one. So we found a 1, 1, and once we do that, the total value becomes 17 minus 9, which is 8, and plus 1, which is 9. Yes. So we reduced to 9. So the total sum reduced to 9. So now the total sum is 9, and so 9 pop out, and the total value is 9. I'll push 1 in, right? I'll push 1 in. Now the top is 5, so 5 pop out. And we say to reach 5, what we need to do is the remaining of 5 is 4. 9 minus 5 is 4. So we say 4 need to add something to 5, which is add 1. So we add 1, which means we'll push 1 in again, right? We'll push 1 in again, and after we do that, the current value will return to 4, because no, return 5, because we will be replaced with 5. So now the current value is 5. And then we do the same thing. Say we have remaining, the largest is 3, so 3 pop out. 3 pop out, so how much we need to, so 5 minus 3 is 2, so 2 needs to plus 1, so we push another 1 in, and then 3 comes out, so the current remaining is 3, right? Now we pop out. Then the next one pop out is 1, then we end it. So we have reduced everything to 1. That's when we say it's good, right? And at any time throughout this process, we have the remaining, right? If the remaining, so we have a maximum pop out, and the remaining, if the remaining is larger than the current, larger or equal to the current max value, then we say it's impossible to create. Okay, let's try this. It should be a fairly straightforward to write. Okay, let's try this out. All right. So what do we have here? Same as usual. Don't forget to use V first, so I can see. Yeah, that's what we need. C. We have 2 hints. Hopefully, we can get this done without using any of the hints. Okay, so we have a target. Now we need a priority queue. So just like from, I just import heap queue. Right. Now we're gonna do heap queue dot heapify. So we need to heapify it. Target. And say while target 0, right, is our target 0 is not equal to 1, right? Then we're gonna say current max is, hold on, it's not gonna pop out the max, it's gonna pop out the min. So this one we have to redo it. Modify target. So that's going to be minus t for t in target, right? And then we're going to say mod target, and so this one is going to be c to the beginning. Mod target. Alright, so for mod target is this current max equals minus heap queue dot heap pop mod target. Right? Oh my god, I spelled target wrong. Dang it. So use sublimes, very handy way. Target. Okay, so now we have this. Actually, we can delete all these. So we have the current max. Oh, the sum. You forgot the sum. So S is equal to sum target, right? Okay, now we have the sum. Say remain equals sum minus current max. If remain is larger or equal to current max, then return false. Okay, now do. Otherwise we say heap queue dot heap push mod target. I'm going to push current max minus remain, right? After that, we're gonna S gonna equal to current max, and then we go back on, pop on the next, blah 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 blah. Once it goes out, right? Once the come out and return true. Okay, let's take a look. Go up, down. Get a little bit here. C. First test case is 935. That is going to be a true. Second test case is 1112. That's going to be a false. Third test case is 8 and 5. That's going to give us a true. Okay, so here we have target, and this is going to be is possible. This is going to be target. Run it. The last one return is not correct. All right, let's try it. Let's see what goes wrong in the last one. 8 and 5. So the first one, oh, I know why. Because okay, so two things. First of all, this is -1. Secondly, when we push, has to be, yeah, has to remain minus. It has to be a minus value. Current max. There we go. Now we pass. Okay, so let's try it here. I'm gonna try some others. Okay, before we submit. I don't know. Just random values. might be a false. We don't know. I just submit it. If it's not right, then we try to find. Come on, come on, come on. I think we have a wrong answer. It didn't do anything. Didn't do anything. Time limit. Ah, we got a time limit. We got a time limit. I shouldn't see it, but I saw it. Oh wow. Time limit. Okay. Makes sense, right? All right, that's fine. That's fine. So we got a time limit. I thought we had a very smart solution. Anyway, so this one is TLE. Okay. Because we want to say if like 10,000. Oh yeah, we do have to make those check first, right? The check I just told you about. If there's anything that's smaller than the sum of the two of all the values, it is 1111. Is that considered? Okay, is that considered to be a valid one? Like this. Is this considered to be a valid one? I guess not. Oh, this is. This is a valid one. But if anything like this, like any value, that's going to be an invalid. That's going to be a false. Probably timeout. Oh, no. That is a true. Because we can always do this. we can replace the same thing. Replace the same thing. But of course, if we do this, that's going to time out. But that is true, right? This is true. Which means we pick out the largest, right? And the remaining, and we just -2. And this one we just -1, -1, -1, -1. Keep minusing 1. Okay, we need to be smarter then. How do we... So when we get the remaining, right, we need to see if the remaining value is smaller. No, hold on. If the remaining value is smaller than the second largest, basically, then we have to push remaining in and then keep going. If not, if the remaining value is larger than the second largest, then the remaining value will still be out, right? And we will still be removing the same value many times. Okay, that's a thought. We can improve on our current algorithm. Which means if we get the maximum out, right, and then we have the remaining, and then we say maximum minus remaining, that will be the value. That's wonderful. That will be the value in here, right? And then it's still the largest, so we use that to minus this again, right? We have to do this, which means every time we get the maximum value out, we need to do a math operation. Isn't that just to get, that's the remainder. We want to get a remainder, right? That's the remainder. Hold on, come again. What are we trying to do? We get the maximum value out, right? And we have a sum. So we do is sum minus current max, and we have the remain. And okay, I want to wrap my head around it. So we have a sum, we minus current max, we get a remain, right? And we say the remain is still too big. So the sum is current max, right? So we want a current max to minus the remain. No. The remain, the ones. So the sum, or the sum minus the current max is the remaining value. So we want to know what needed. So it's the current max minus remain, right? Current max minus remain is the value we're going to push in. So it's this value, current max minus remain. If it's still too big, then we need to do because now current max is a new sum. So it becomes current max minus current max plus remain, right? That is, we return to the same remain, right? That's the, because S becomes the current max. And we have the new current max, which is this. So that becomes a remain. I think this is not right. So get something very large, and then we say minus this, so it's going to be a large value. So it's this plus this equals this, right? And then this is very large. Then we say the sum is going to be this. We're going to minus this again. Why I couldn't write a good formula out of this? The sum minus current max equals remain. And what we're going to do is the new value is going to be remain minus current max. Right, that's the value we're going to push in. Oh, it's not remain minus current max. Current max minus remain. Right, current max minus remain is the value we're going to push in. And now we have a new max, a new S is equals to current max. And the value we want to achieve is this. And we're going to say S minus current max, which is S minus, so it's S minus current max. So it becomes remain. And remain is smaller than current max. And then we're going to yes, the remain doesn't change. The remain does not change. Each time it's the same remain. Yeah, remain doesn't change. We just do it many, many times so the remain doesn't change. But what we want eventually is going to be the remain current max minus remain. So every time current max minus the remain is everything minus the current max. Is the remain, okay, the remain, yeah, of course the remain doesn't change. Remain is the rest. That's what remain is. Remain is the rest of the value. And just every time we're going to do the sum, right? The remain, the current max minus the remain, right? Current max minus the remain, we put a new value in it, and this minus the remain again. So every time we do the exact same thing, right? The current max minus remain. So that means we can do it many, many times. Eventually, we're gonna get what's that? What's that we're looking for? The word that you're looking for. The word I'm looking for is remnants, right? The remain after we do a division. So it's going to be what? Who divided by whom? Current max coming out, right? And then we're going to say the current max minus the remain. And then this is going to minus remain, this is minus remain, minus remain, blah, 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 until what? Until if minus remain, we get the new value, and then this one minus remain, we get a new value. We keep minus the remain until we can get a remnant, right? So this one minus remain going to be a value smaller than we put this in. But what if we can divide? Like this situation, it can divide, right? This one actually does not divide, but this one divides. It divides the remain. If it divides the remain, but we cannot allow it to divide the remain, right? So the smallest you can go, no, we need to go all the way down to some value that is smaller than remain. No, not smaller than remain, smaller than the second largest of the remain. So we divide remain, right? And then we can get a quotient and we get a remnant, the remainder, that's the word. We get a remainder. And if the remainder is minus this and remainder is smaller than this, then that's good, right? But the remainder, if we can get to 0, right? What does happen if we get to 0? Yeah, what do we happen if we get to 0? Like 114. What do we happen? So current max is 4, sum is 6, so minus 6 would be 2, right? And 2 is still, so when then 2 come up with 4. 4 minus 2 is 2, and 2 minus 2 becomes 0. It becomes 0. Yeah, so 112 will be a good example. 112. Should that be like a false? Hold on. Is 112 a false? 112 is a false. But 12 is a true. Okay, 112 is a false because the remainder becomes 0. But 12, or we consider that as a special case. Because if we have more than 1, right? So what we're saying, we get the max out, we get the max value out, right? And we have the remaining value, and then basically we just say how many times the max can take away the remainder. Right? We take it once. If it's still the max, we just basically take out the same thing, and we take out the same thing, until we cannot take out any more. And it will happen, right? The remain will be the same value as whatever in the front, right? The sum of whatever is in the front, the same value. When that happens, the only way to reach here is say, yeah, now it becomes 0. Then it's a no good. However, we have a special case in this, because when we get to 1, which supposedly is not good, but now it is actually good. So in that sense, right? In that sense, when we get out the max and we get out the remain, right? And what we do is to find, well, we actually don't call it remain. Remain is going to be the current max, and this remain. Or let's make it more explicit. So this is the remain, and we have the R is going to be current max to this remain, right? So then depending on the R value, right? If R is 0, and when that only happens if we have 2, right? Only have 2, so we can check it here first. We say if len target is equal to 2 and min target is equal to 1, then we return true no matter what. So like this, if len target is equal to 2 and min target is equal to 1, then we return true regardless. And this is not the situation, so we say if not R, then we return false, right? Or if not R, actually we can do this first, because if remain is larger than or equal to max, and then when we do this, we'll return a max. So we're gonna do this first, right? So we can say remain is this. So if remain is larger than this, there's no go. Oh, that covers. It actually doesn't cover. So remain is larger than this is a false. And then we do this and say if R is equal to 0, that's a false. And then if none of these happens, then we push in minus R, right? Minus R. And now S is not equal to current max. S is going to equal to remain plus R. And then we go back. The last one doesn't pass. Okay, let's see. Let's see where we got wrong. So we have 8 and 5, right? So 8 and 5. So it come out, current max is going to be 8. Remain is going to be, sum is 13. 13 minus 8. Huh? That doesn't make any sense to me. Current max is 8, right? So the remain is The remain is 5, yes. The remain is 5. Remain is 13 minus 8. Remain is 5. So remain is 5. And remain is not larger than, so r equals current max is 8. And we do remain, that should give us 3. Right, r is 3. So we push minus 3 in. And the new sum is going to be remain. So 3 plus 5 equals 8. So sum is s is 8. Coming here, pop out. It's going to be 5. Pop out. 5 pop out. Remain is going to be 8 minus 5. Remain is going to be 3, right? And then remain is not larger. And we do this. 5 do mod 3 give us 2, right? So current r is 2. So we push 2 in, right? We push 2 in. And then that's going to be s going to be 5. So coming back up, 3 pop out. Current max is 3, s is 5, so remain is 2. And remain is larger or equal to current max? No, current max is 3. And r equals 3 to 2 is 1, right? Is 1, so we push 1 in. Now we remain is going to be r is 1 plus remain is 2, so it's going to be 3. So remain, sum is 3, and we have a 2 and a 1, so we got 2 pop out, right? And 2 pop out, remain is 1, remain is 1, and if remain is larger than this 2, no. And then, here, current max is 2, remain is 1. So I think it's whenever the remain is 1, we say remain is 1, which means if remain is 1, we just say that's true, right? We return true. Because remain is 1, the only chance of remain is 1 is this situation. So we're going to have a check here. So we don't have this. We don't need this then. We just say current max remains this, right? And we say if remain is equal to 1, then that's a true. No matter what, we have remain is 1, which is just excluding the current max. Everything else add up to 1. That's the only chance that's happened is we have 2. So if it remains 1, we return true. If it remains larger than this, we return false. And we do this, and then we say, let's make more explicit. If r is 0, then we return false. And then we push. And then these will pass, including, right, including the new test cases. No matter how many 0 you put in there, it doesn't matter. This is going to be true, no matter what, right? So let's try it again. So first of all, I want to delete this line and try this again. See if I got better luck. Pending. Runtime error. We have a remain as 0. Oh, a single value. A single value. That's a single value. A single value will have remain as 0. Why is this not detecting that? S is going to be 2, current max is 2, remain is 0. A 0 larger than, oh. So we have to add it here if remain larger than or remain equal to 0. Wow. typical situation here, huh? I mean, it should be anything should be false, because if you have a single value, it's you add it going to be 1, adding going to be 1, adding going to be 1. It's not going to be, which means we can say or remain equal to 0, right? Let's say here, so we say largely equal to current max or remain equal to 0. Then it's gonna be false. Yeah. Wow, I never realized it should be like different. It's gonna be all be false. So in one situation, we have two situations. These are like edge cases. But if we have a 1, right, then that shall be true. Yeah, that shall be true. All right, try it again. Judging. There we go. We got it. Wow. Took a few tries. Let's check. What's the runtime? I think this runtime should be O and login. A worst case scenario, right? O and login. We check every single time. It should be check every single value, and then O and login. I think that's the runtime. Oh, I got pretty good. Runtime. All right, so we solve this problem in reverse. We find the largest value first. We find the largest value in target and figure out how can we reach it. Now the only way to reach the largest value is for the previous round is that in the previous round the value sitting at the same position as the current largest value is sum minus current max, right? Sum minus current max. So we have that, and and that is how we resolve the current max. Then we find the next max and perform the same procedure. This continues until we end up with all ones, or when sum minus current max, sum minus current max is a remain. No. The value setting at the same position as the current max, as the current largest value, is sum minus current max, that's the remain, and gonna be current max minus that, right? Current max minus sum minus current max. So this is a remain, and current max minus remain. That's basically 2 times current max minus this, right? Value is current max minus sum minus current max, which is the remain. Current max minus remain is the value. Let us call that. Let us call sum minus current max equals remain, and current max minus remain equals R. If R is larger than 0, then we can continue. We can replace current largest with R and repeat the same procedure for the next step. Otherwise, we declare that it is impossible. Right? We tried this straightforward solution, but got TLE for this test case. All right. Apparently, by performing current max minus remain every single time we are wasting resources because current max can be gigantic while remain is very small, right? In this case, each time current max minus remain happens, we will end up with an R that is still the max of the next iteration. So essentially, what we need is to compute current max mod remain. Right? Current max mod remain. This way, we can directly arrive at an R that is smaller than that is, I shouldn't say smaller, that is that can save a lot of iterations. However, there are tricky edge cases. First tricky edge case is, first of all, if remain equals 1, then current max do remain equals 0, which technically speaking is a failed case, since we cannot replace any value in target with 0. However, remain equals 1 is a special case, which only happens when there are there are 2 elements in target, right? Only have 2 elements in target, and whenever one of the 2 elements is 1, it is immediately possible. Another edge case is when remain equals to 0, which can happen when target is of length 1, right? Target is of length 1, and it's very important to check remain equals 1 first. And it's important. Yeah, must check. Oh, hold on. But how about 1? Remain will be 0, and then we're going to return false. Hold on. That is not considered. How is this one fair? That's true. How? Sum is 1. Oh, we come out here. Okay, no, that doesn't matter. Edge case is when remain is 0, which can happen when target is of length 1. and the element is not 1. In this case, we will enter the while loop. We'll enter the while loop, but end up with remain equals 0, and this is an impossible case. Once these two edge cases and the mod operation is used, the problem is resolved. Is solved. So I think it runs in O and log n, right? Because worst case scenario, I will say every single element inside target will be run once, and each time when we pop, that's O log n. So added together is O and log n. And we have a fairly good runtime, which come up to 84%. I think this is another example of thinking in reverse. Right? I was trying to think forward, how to make it, but it's not working. So we think in reverse. Let's take a look at a hint. What do we have in the hint? Sum is really increasing. Yes, largest element must be formed in the last step by adding this total sum in the previous step. Thus, we can simulate the process in a reversed way. Exactly, that's what we have done. Subtract the largest with the rest of the array and put the new element in the array. Repeat until all elements become 1. Exactly. So we follow, although we didn't see the hint, but we follow exactly the same thing. Okay, let's take a look. I think this is. Do you think this is a hard question? Well, it could be. Dear LeetCoder, LeetCode interview just got featured in Product Hunt. What's Product Hunt? Oh, pressed the wrong key. LeetCode interview. What's that? Online coding interview platform for professionals. Hold on, what is this? Oh, you can do your interview directly. Is that what it is about? What is Product Hunt? Product Hunt. What is Product Hunt? Product Hunt. Is that for company to search? Is an American website to share and discover new products. Oh, share new products. To share new products. So they have a new product, LeetCode interview. All right, just a little bit deviation. Don't really want to learn. I mean, it's fine. Maybe, yeah, people can use that. Company can use this for sure. All right. Oh, it's listed as hard. Okay, then we have, yeah, I do think it's probably a hard one. I have to think in reverse. All right, let's see. Backtrack. OJ is wrong. Update of February 26th. Doesn't do its work at all. Some would rather believe in the see. Oh. Ah. Oh wow, these test cases are offered by Lead 215. Oh wow. Yes, yes, that's true. Without is wrong. Yeah. A is 1 or total is 1. If A is smaller than total or total equals 0, or this equals 0, yeah, total plus, yeah, he got pushed, yeah, it's the same thing. Oh wow, so he pushed, wow, oh my god, he is good, right? Oh wow, so he pushed for these test cases. It's a harsh language though. Fail the case, which you expect true, yeah. Wow. Okay, let's read again. Total sum always bigger than all elements. We can decompose the biggest number. Yes, each round we get a current max value deleted by the sum of other time on to build up the priority queue time log max a log n for the reducing value part, and we have O max a loops, which is similar to the GCD space on. I think it's more complicated, huh? Why is that? Log max a logs n log n. Why would it? Oh, you consider the percentage as log max a? O max a loops. I don't understand that part. Yes, but like I said before, I agree. The percentage operation is much more important. If brute force solution is accepted, then the solutions without percent are right and good. But the truth is that solution without percentage should be TL. Yes, because like I said, this one we're just going to keep going. Yeah, and I think we have similar. We call it total. I call it S, right? And then I take the total out. I call it remain. I have true, but have total equal to 1. I have while true. It's the same. A smaller than total, which is remain larger than current. Yeah. Have total equal to 0, which is what is total equal to 0? The remain equal to 0, or this equal to 0, and then we push A into it. Wow, no words. This is truly amazing. Truly amazing. So it's because of him. It's because of him. Amazing. Amazing. All right, I want to see complexity. It happened that with these values, working time will be not a proof. N plus log t times log n is the size of the target. T is the biggest number among target. Which is the same as what Lead 215 says, right? So log n is this part. And why you have a log t? Because no, I think it's not about this operation. It's because you push something else in. And depending on your max value, right? Depending on max value, and then when you're reducing the max value, I'm gonna say It's not unlog. Well, unlogin is definitely the upper bound, right? We're not wrong in that. It's just how many times we go through the loop. That is the question, right? That is the question. And then what they say is the number of times you go through the loop is not n times. It's actually lower than that. It's log t times. That's what they say. Instead of n time, it's log t time. I don't know. But I'm gonna. I'll write a few more comments because just to notify what this question is about. But good. I mean, never done this before. Yeah, we solved it. It's a hard one. It is a hard one. All right. I'm gonna keep writing some comments, but that'll be it for today. See you guys tomorrow.